Okay, we're on, are we? We started? Okay, I'll share my screen. So, can you see that?
Not yet.
Oh, okay. Not better?
Yep.
Yeah, all good.
Okay, so we're up to ventilation systems, and you both had a fair bit of experience with this now, but we'll, for the sake of just going through the basics, we'll just work through this. So we're up to ventilation. Every building has ventilation in some way or another, as you're aware. Typically outside air, toilet exhaust, could be kitchen exhaust, car park supply, and so on. The job you're working on, Dewar, would have lots of other systems as well. You'll have pool exhaust and things like that. The NCC, just we're going down to basics here. So you may have been over it, but John, you probably haven't. So I think it's worth just going through this. In the NCC, there's in part F4, it talks about natural ventilation and mechanical ventilation. Basically, it says when you need to have ventilation. So I'm going to try and put that up and we'll have a look at it. So I'm going to go to, I'll just check that page 272. Okay, so is that clear? You can see that, NCC?
Mm-hmm.
The reason I'm putting these up is because you need to be familiar with these things over time, so and know where to look. So part F4, 4.5 of the NCC says that a habitable room, because that's in italics, that means there's a definition for that. Have you come across that? There's a whole set of definitions in the NCC that says, what is a habitable room, for instance? And you can look at that and say, okay, habitable room, generally speaking, is where people congregate. So it might be an office space or a meeting room, anything like that. So these rooms need to be ventilated. However, a storeroom where you're just storing equipment or files is not really a habitable room. People go in there to get things, but they don't spend time in there. So a room like that doesn't have to be ventilated. It can be, but it doesn't have to be. So sometimes a client might say, look, I've got paper stored in this room. I want to keep it at a reason. I want to have some ventilation just to keep the moisture down and move the dust and whatever. Then you can ventilate it, but you don't have to. So it says part A there, natural ventilation. You either have to have natural ventilation complying with F4.6 or mechanical ventilation complying with AS 1668 part 2. Okay, so we mentioned that plenty of times. I just wanted to mention natural ventilation. You can have natural ventilation where you've got an openable window or door in a room. So such as in a house, you've got a bedroom with a window. You don't have to mechanically ventilate that. You've got natural ventilation. A bathroom can have natural ventilation as long as you've got a window that you can open, and so on. So that's covered in F4.7. You can read through that when you have some time. Sorry, 4.6. The opening has to be 5.5% of the floor area of that space, or 1/20th. Okay, so if you've got an area that's 20 square metres, you need 1 square metre that can be opened. F4.7 talks about ventilation borrowed from an adjoining room. Now, this might be useful. You've got to read through this, but just as an example, say in a residential apartment, you can, if you've got a bedroom, adjacent to a living area, you can borrow ventilation from the living area, provided you've got enough openable area. So the living area has to have 10% openable, and then the bedroom has to have 10% as well. But you just have a read of that and be clear. It depends on the class of building, and we've talked about classes of buildings before, I think, haven't we, in the BCA? That's another important thing to, you're not going to remember it straight away, but just go back and have a look at it. Class 5 is an office. Class 6 is shopping centre, and so on. So you need to be aware of those. Class 2 and 3 are generally what you're dealing with residential buildings. So get familiar with all those things. Now we'll go back to the notes again. So AS 1668.2 provides information to enable calculation of ventilation flow rates. Now, I'm sure Dua has had a fair bit to do with this, but I don't know whether you have, Jelen, so I'll just bring that up. In the Appendix A and B, there's a table of different types of areas. You've seen this, Jelen? Sorry, Dua, have you seen this?
Yeah, absolutely.
Jelen, I don't know whether you have, but this is an important thing to get used to in 1668 Part 2. So there's all these different areas. So let's take, for instance, go down to let's have a look. General areas, for instance. Corridors. It says here to provide 1 litre per second per square metre of floor area. Now that's outside air. This is referring to the amount of outside air that you're bringing in. So for corridor, that's what they're saying here. Dressing rooms. Now the first column is floor area per person. So if you don't know how many people are going to be in there, this gives you a guide on how many to allow for. Okay, and then the outside air quantity, and then litres per second per person. So you've got 2 square metres per person and then 10 litres a second per person of outside air. Okay, so have a look at that. You'll use that very often in your work. Now this is Appendix B. This now talks about exhaust rates. In the absence of any other information about exhaust requirements, this tells you what you need to allow for. So, for instance, a garbage room and service compartment, 5 litres a second per square metre of floor area. And then it says in the comments, you need at least 100 litres a second per minimum, sorry. So most residential buildings, particularly the high-rise ones, have a garbage room. So you need to either ventilate that. Quite often they're air-conditioned because in the warmer weather, the rubbish goes putrid pretty quickly. So they quite often air-condition them just to control that, to control the rate of rubbish going off because it gets very smelly. So we'll continue on, but you need to be very familiar with those 2 tables. Now, mechanical ventilation generally comprises ductwork and fans, as you know, may include filters and other components. When you've worked out the ventilation requirements and calculated the flow rates, you can begin to size the ducts and fans. Okay, pretty basic. Now, I've mentioned there natural ventilation may be applicable to rooms on the perimeter of a building which have windows and doors, which we've just talked about. Now, air distribution. Ductwork is used to move air in HVAC systems. The motive force pressure is provided by fans inside the air conditioning units or ventilation fans connected to ductwork. So you've seen drawings, you know what I'm talking about here. Common air systems in a building include air conditioning supply air, return air and outside air, toilet exhaust, equipment rooms supply and exhaust, energy recovery ventilators. Have you come across any of these, you guys, energy recovery ventilators? Dave?
Yeah.
Good. Okay. Now these are mentioned in the NCC as well, and I'll come to that a bit later in Part J5, where there's a requirement to provide that. Ductwork is normally constructed from galvanised sheet steel and formed into rectangular sections. That's the most common, or circular or oval shapes. Other materials can be used. Stainless steel is sometimes used if you've got a corrosive environment. Now, when you're working with an aquatic centre, you'll have to look at the materials you're using there, because the air can be corrosive in aquatic centre.
We used fabric as well.
Oh, using fabric. Okay, for supply air.
Some parts. Yeah, for some parts.
What about your exhaust?
The regular galvanized steel from the rooms that we had to work with.
Just if you've got, usually for a pool, is it an air-conditioned space, the pool area?
Pool areas are mostly external, but the internal areas are air-conditioned.
Yes, okay. So the internal areas, you'll probably have a special air conditioning, a pool air conditioning system, will you? Pool air conditioning plant with an energy recovery ventilator in it and those sort of things.
Yeah.
So the air that you draw back from the pool is corrosive because it's got chlorine in the air. So usually the ductwork back to the air conditioning unit will be stainless steel, and the air conditioning unit itself will be made from stainless steel to stop the corrosion. So just be aware of that. If that's not shown on any drawings you've got, it needs to be raised as an issue, because galvanised sheet steel in that environment will rust very quickly. And so you need to use stainless steel, or you can use plastic, but stainless steel is what's normally done. Okay, air outlets. The different types of outlets that we commonly see for supply air, you have louver face diffusers, swirl diffusers, sidewall grills or linear slot diffusers. There are lots and lots of these. You need to look at catalogues to get a full idea of the range. Return air grills are normally egg crate or half chevron. Half chevron has got a bit of a bend in it, so you can't see straight through it. Exhaust grills are normally egg crate type. Weatherproof intake or exhaust louvers are commonly single stage, but they can be multi-stage. The NCC sets out maximum pressure drops for louvers. So you need to, when you're doing your fan statics, you need to look at the NCC. I think for a single stage louver, it says 30 pascals. So don't go over that. And then the louver has to be selected to comply with that. I've made a note here, big part.
Why do we want to use a multi-stage louver? Is it to stop sand from coming in, or rain, or are there any particular uses?
It's mainly for rain, but you don't really need to. It's not. Look, sometimes an architect might say he wants a two-stage louver for some reason. It might be just for appearance, but a two-stage louver creates a much higher pressure drop.
Yeah.
So, and usually the weatherproof louvers on the outside of the building are an architectural feature, not a mechanical thing. So the mechanical contractor quite often does not supply the weatherproof louvers. They'll be supplied by the builder in accordance with the architect's requirements. So as engineers, we need to know what louvers they're putting in. This can be quite difficult to find out, actually. And, you know, I've many times had to ask the questions to try and find out what they're using. They keep changing their mind. But the NCC now says that the pressure drop cannot exceed 30 pascals for a single stage louver, etc.
Yeah.
So you need to communicate that with the builder and say, look, this is the maximum pressure drop we can have, and keep asking questions till you get the information. It can be quite frustrating. That's one of these things that's hard to get information, like it is with glass, which you've experienced. But you just have to keep asking because you want to get the right information so you can do the job correctly. Okay, so moving on to preliminary design layouts. This is the next step in the process, is to set out the location of all the outlets on a drawing or a sketch. All the supply air outlets, the return air outlets, and so on. And then you can start, once you've got the outlet shown on a drawing, you can start to connect all those up in a system, and then you can move towards sizing the ductwork. The preliminary layouts can be hand-drawn sketches. Back in when I was my early days of work, everything was drawn by hand. So we'd do sketches by hand. But then programs like Bluebeam came in, which makes it a bit easier. Or there's Revit. Now, I think what Philip and Ivan are wanting to work towards is for you guys to learn how to use Revit so that you can produce your preliminary drawings using Revit. And the benefit of that is it'll be a much more efficient process because the workshop drawings are being done in Revit. Your preliminary Revit sketches can be transferred to the drafting people, and they can just continue to develop your drawings. If you do a Bluebeam sketch, it's just a throwaway for them, really. They can see what you're looking for, but they can't really use that. You can't take a Bluebeam sketch drawing and turn that into a workshop drawing. It's just, I don't think, well, when I was working, you couldn't do that. I don't think you can now. Anyway, so that's the plan, to learn, for new people coming in, to learn how to use Revit. You're familiar with LOD, or level of detail? Have you come across that term? Duan is aware of it. So preliminary Revit drawing would probably be classified as LOD 100 or 200, just depending on how much information you put on that drawing. The higher the number, the more detail is in the drawing. You can look these things up. You can Google LOD 100 and you'll get a summary of what each of those typically involves. The highest level, as far as I'm aware, is LOD 500. So what you're getting into a BIM area, which is building information modelling, and normally we wouldn't go to that level. We'd probably go as far as LOD 400, perhaps. Shop drawings used to be LOD 300 or 350, but now maybe 400, which means when you're getting into 400 or 500, there's linkages. I'm not a Revit expert, but there's linkages from everything on the drawing. So if you click on an air outlet or a piece of equipment or something, it brings up a table of all the information relating to that equipment. Okay, so if you had an LOD 500 drawing, it's basically got every bit of information you need about everything on that drawing just by clicking on that icon. That's pretty powerful, and I think it's exciting, to be involved in that development. Not for me, but for you, because I'm not going to be involved too much in that, I don't think. But as you go on, all these developments are fantastic to have all that information available at your fingertips. So you don't have to go and look for other information. And I think, I'm not sure where Philip's up to, but he is developing a Revit training module to some degree. I won't be involved in that because it's out of my expertise. So now we come to duct sizing. Once you've got your preliminary layout done, you can start to size the duct. You've got all your outlets connected. You need to allocate air quantities or flow rates to each outlet, which comes from your basic design. For an AC system, the total supply air flow will normally be the supply air flow rate from the camel output. But just be aware that like when you do a camel load, you can select a type of system that you're going to use. So you can say it's going to be a VRF DX air-cooled system, and then it'll calculate the loads based on that system. But when you go to select the equipment, the equipment from the manufacturers doesn't always line up with what your camel program says. So you work out you need a 10 kilowatt unit, and Camel says for that you need, based on their calculations, you might need, let's say, 600 litres a second. But when you look at the equipment from Mitsubishi or Daikin or someone, it says for that unit, it's 1,000 litres a second. You just need to be aware that there may be a difference there, and you need to use the air quantity that's given to you by the air conditioning manufacturer. Okay, so instead of being 600, it might be 1,000. And then you might have to size your ductwork based on that. I'll just mention that so you're aware of it. If it's a chilled water system, which you guys are not really doing much of, but when you come to that, and you will, then the Camel supply air will normally be the figure that you use. And you select your equipment based on the Camel airflows. For ventilation system, the total air flow will be the sum of all individual areas served by one or more fans. So for a toilet exhaust system, you know where all your toilets are, you know how much air you need for each one based on your 1668 calculations. And so you can allocate the air to each outlet and then work out the duct sizes. So when you're coming to sizing the ductwork, I presume that you're using a ductulator. I'm just going to bring this up. Hold on. Can you see that on the screen? The ductulator?
No.
Yep. Okay, so you probably use those back in the old days when I started work. We used to do it manually. We had a ductulator, which was a pretty fancy thing. You could swing around and get the size. It was quite good actually, because it gave you.
Well, you needed a good vision to find the numbers.
Yeah, but it gave you a range of sizes for a particular airflow and pressure loss. Anyway, so but you'll be using that little calculator there, I presume. Just be aware again that the NCC has certain requirements about sizing ductwork. Now, I'll just see if I can bring that up and have a quick look at that. And so if we go to, what page number was it? 365. Okay, so this is part J5 of the NCC. I've mentioned this a few times, and I'm going to keep mentioning it because you've got to get this into your head, right? It's really important. There's a lot of stuff in here that you need to be aware of. Some things may not apply right now to what you're doing, but eventually you'll need to know all of this, and I'm not going to go through it now because we're just about run out of time anyway. But going down to, there's a section on mechanical ventilation. We'll go a bit further. Fan systems. There's a lot of complicated stuff here about fans, and Jelen and I talked about this the other day, about whether a fan has the right efficiency. When you select a fan, it has to comply with the efficiency requirements of this part of the NCC. And the fan suppliers are aware of it, and they'll tell you whether or not their fan complies, but basically the selection should comply. I'd like to talk to you a bit more about that later, John. Perhaps if you can hang on after we finish, we can just have a quick chat. But going down through here, there's page 368, point C, ductwork. This talks about the pressure drop in the index run can't exceed 1 Pascal per metre. Okay. Flexible ductwork must not be more than 6 metres in length, etc., etc. So have a read of this. As you go down, part D, ductwork components in the index run, and it gives you pressure drops for various things that that apply. I think we've talked about this before. But you want to have a look at this each time you're doing your statics just to make sure you're complying with this. Things like 0.7 attenuators must not exceed 40 pascals. Single stage louvers 30 pascals, two stage louvers 60 pascals, etc., etc. So there's a lot of stuff here that you can use in your static calculations if you don't know anything about the equipment. For a weatherproof louver, for instance, so you can just say it's got to be 30 pascals. That's it. Until you know more about it, that's what it is. And an attenuator, if you don't, well, you don't know the selection of the attenuator when you're doing your statics. That'll come later. So you have to put 40 pascals there. Okay, that's all you can do at this stage. With grills, it's got supply air point X. Supply air diffusers and grills must not exceed a pressure drop of 40 pascals. To me, that's very high. And exhaust grills must not exceed 30 pascals. That's very high. If you're using an egg crate grill, the pressure drop really shouldn't be any more than about, probably less than 5, actually. But you can look it up. I've mentioned in those notes Shape Air. You can register to access their catalogue, and it's got everything you need to look up to make a selection of a diffuser. It's worth doing a couple of times just to get a feel for what it should be, because you don't want to oversize the static too much because it affects your fan selection. Okay. So then we get back to fan static calculations. So you can see that a lot of the work at the moment involves fan static calculations, peak loads. They're the basics of what you're going to need to know. I don't think I need to talk any more about fan static calculations, do I, at this point? I think we've talked about that enough. Unless you've got any questions there.
I can think.
All right, so once you've done the fan static calcs, you know the airflow, you know the fan static, you can select the fan or the fan for the AC unit. And then when you've got that information, you can prepare the equipment schedules. Okay, so we're back to equipment schedules again. So that sort of revolves around these things that are very important that we do almost every day.
Yeah.
So we've got the fan static calculations done. You can complete the equipment schedules for the AC units and fans. And the calculated static will enable selection of the appropriate or correct fan to deliver or extract the air to and from the outlets in the system. So when the schedules are complete, they can be submitted for approval and or sent to the equipment supplier to confirm requirements. And as we said last time, these schedules are very important. They carry right through the project. You can update them as things change, or you add fans, take fans away, or air conditioning units are added or taken away. And everybody's looking at those schedules. The drafters are looking at them to see what's the latest equipment, what the airflows are. The guys on site need to know what the latest equipment is, so when it comes to site, they can allocate it to the right position. The engineers need to know, so that you can keep up to date with what's going on with the equipment. The project manager uses the schedules to order the equipment. The commissioning guys use the schedules so they can prepare their commissioning programs and understand what they have to do. And then they become a record of the project when they go on the O&M manuals. So you can't stress anymore how important they are for the project. And some of these things that we do are a bit tedious, repetitive, but they are very important. So this is the whole process of what we do, of peak loads, fan static calculations, preparing equipment schedules. It's just fundamental stuff. So I just want you to appreciate that when you're doing these, I know sometimes that, you think, oh, it's getting a bit tedious doing this. There's a lot of people who benefit from what you're doing, and the project can't proceed or can't get built without the work that you're doing in preparing the fan statics, the heat loads, and the equipment schedules. So feel good about it. You're doing a good thing. Okay, we'll stop there. Any questions?
All good for me.
Okay. I know next week's your last week and you're going to be very busy, I suppose, right up till Thursday. Do you want to have one more session next week, or we can have two if you like? We can go Monday, Tuesday, or just say Tuesday.
I
We
won't
can
be
continue.
here on Thursday, so
Okay.
yeah.
Well, do you just want to do one on, say, Tuesday for half an hour? And we'll keep
That
working
sounds
through
good.
this.
Yeah.
Yeah,
Yep.
that sounds good. Yeah.
Tuesday at 9:30.
Yep.
Yep.
Okay. I'll send an invitation out. But I'll be here anyway. So if you need to talk to me about anything, just let me know. And I'll be here at the usual times. And I'll be here on Thursday as well. Well, I'll be available. So you won't be here, gentlemen, but if you need to talk to me, do it. I'll be here.
Yeah.
Okay.
Thank you.
Thank
I'll
you.
just
All
stop.
right.
Um,
Thank you.